So good evening, everybody. Welcome to another Thursday night chat clinic. Thank you for joining us. There's only 5 of us in at the moment, but that's okay. I'm planning to complete the Onshape demo that I was doing back in September. I never got around to finishing that, and so I said, I'll just start that tonight and do that, and also use it as a chance to answer any questions that people might have about Onshape or anything else at FTC. With us tonight is again Joe Varnell. Hello, Joe.
Hello.
Joe is our first senior mentor for North Texas, and so he helps with all of the different FIRST programs that exist, and I'm always happy to have Joe here. And he often covers for me when my internet connection dies, which it seems to die pretty regularly at about 7:50 on Thursdays. So we'll see what happens here in about 50 minutes.
What happens at 7:50?
I don't know. I honestly don't know, but last night it died at about 9:45, but sometime in the evening my internet connection just dies, so I'm not sure exactly what that is. Anybody else on the call want to say hello or have a question or anything before I start with the demo?
I've got lots of questions, but I'll try to give you a chance to answer them first.
Are they questions about what?
Oh, they're about your topic. I've been working ahead and run into some walls that I want to see if you answer them before.
Okay, that'll be great. I'm glad I'm doing this then, and I'm glad you were able to join us. Anybody else?
Hi, this is Peter Lee. I'm first year. Actually, our team is a first year team, 18227.
Welcome.
Yeah, so actually I got this information from Coach Fan of 86, yeah.
8565.
Yeah, 8565, yeah. So I watched your recording of the first video of building that mechanism, wheels, chassis. So I'm interested in keep watching, and also I have a question on how to make the wheels alignment, when they mount it to the chassis, how
right.
to make all of the wheels aligned really well.
Okay. I'll look at that today. We'll look at some parts of alignment, and then if by the time I get to the end I haven't answered that question satisfactorily, just ask again, and I'll show some more of it. There's two parts to the alignment. Part of one of it is front to back, where the axles are, and then the other part is aligning on the axle. And I'll show both of those briefly.
Okay, thank you.
Yeah, you're welcome. But thanks for letting me know, so I'll make sure to cover that. And welcome, by the way, to your team. We're always happy to see rookie teams. This will be an exciting season, so welcome aboard, and whatever we can do to help, good. And I'm glad you're already in touch with 8565. They're a great mentor team, so they're really good to be in touch with. Anybody else? Just a minute. I'm going to pull up the video just so that everybody has a sense of what it is that we're building up to, just of the robot that is being put together. Where is my video? There we go. And let me share the screen for that. So share screen, and let's do this one, share. Hopefully everybody will be able to see my screen. Oh, I should probably switch it to be able to optimize for a video clip. And let me just go ahead and play this video. So the drive that we're building looks a lot like this. Right, so it's a mechanism drive. It's pretty small. It's using the Rev Robotics wheels. It can drive sideways, and it can turn and all sorts of different things. It's reasonably fast. And my goal for this was to create a mechanism drive that used almost entirely Rev Robotics parts, because many teams are getting the Rev Robotics kit of parts, and I wanted to make a mechanism drive. Rev Robotics also sells the mechanism drive kit that they have, but I wanted to make a mechanism drive that was in the style of the way 7172 has done their drives in the past few years, because we've had really good success with them. So that was my personal goal in designing this robot. And so I did that, and then I originally did the CAD in Fusion 360, and then I decided for to try it in Onshape CAD, because that's another CAD package that many FIRST robotics teams are starting to use. And to just a minute, I've got to get my windows back here. There we go. That's another CAD package that FIRST robotics teams, FIRST Tech Challenge teams are starting to use, and it seems to be pretty capable as well. And it may be a little bit easier to get access to Onshape CAD. Onshape CAD runs in a browser also, so it's not limited to just Windows or Macintosh computers. It can just run in anything that's able to run in a browser, and that includes things like iPads and Chromebooks. So that's a very nice feature of Onshape CAD. So let me find my screen here. Oh, there it is. My screens keep popping all over the place here. So, all right. So let me go ahead and switch to my Onshape screen. And if at any time I forget to switch screens or you're not able to see what's happening, then please just let me know. But we should be seeing Onshape now as the, and this is pretty much where we had left off at the end of the last video. So we had gone through and done the connections needed to join the rev extrusions to the channels and to create the dead axles going across the thing. Now, again, from the previous video, if you didn't see the previous video, then probably go back and look at it. But these axles are different from the way that it's often done in robotics, where the axles are fixed, they don't spin. And so the wheel will end up spinning around the axle, which is different from the way it's often done, where the axle spins and makes the wheel turn. I'm going to switch off of sharing the screen real quick and go to just a quick demo of things. So let me switch to my overhead camera. So what we're looking at is, oops, I didn't switch. There we go. So what we're looking to do is to have a wheel like this, and this is the rev mechanism wheel. And instead of the axle turning to make the wheel turn, the wheel has bearings in it in this design, and the bearings enable the wheel to spin even if the axle's not turning. And so the axle can be completely fixed in place, but the wheel is still able to turn. And then a chain will be used to turn this sprocket, and that's what makes the wheel turn in response to a motor. So that's a dead axle design. It has some advantages over the live axle designs. Most importantly, one of the big advantages is that on the robot itself, the fact that this is a dead axle gives a lot of rigidity, a lot of structure to the robot to be able to hold the axles in place, and they're pretty much guaranteed to stay level. They're not going to slip out. Things aren't going to slip off, things like that. So to look at what we're going to need to build that, if I just take this wheel structure and say, well, what are the parts for it? I'm going to take the wheel off the shaft here. What are the parts that make this wheel work? Let me just pull them in one at a time. I don't have an easy way to get there. We go. Stay there, wheel. Actually, let's say if I turn it this way, stay there, wheel. Stay. Wheels for some reason like to roll away. So what it consists of is there's a mechanism wheel. This is the rev mechanism wheel that is there, and you can see it has mounting holes in it. And one of the things that's unique about the rev wheel, which can be a feature or it can be harder to deal with, is that the mounting holes are in a well inside the wheel. They're not flush with the face of the wheel or with the edge of the wheel. So that's part of the reason why we need a spacer. So attaching to that wheel is going to be a spacer. And this role of the spacer is twofold. One is it's going to be able to get the sprocket, which will go next, away from the wheel. So that's the first role that it has, is to be able to get some clearance between the chain and the sprocket and the wheel itself. The other purpose of the spacer is that it's going to hold the bearings that enable the wheel to spin around the axle. And we don't want to just have the plastic itself on the axle, because that's not a very good bearing, for one. And for another, it'll eventually wear away or break or things like that. So we really want to have a set of bearings. The bearings that I chose to use are these ABEC 3 bearings. And let me let me get a closer view of the ABEC 3 bearings like this. It's an 8 millimeter inner diameter, a 12 millimeter outer diameter, and 3.5 millimeter width bearing. And so that is going to end up on the inside of the spacer. And then inside of that are these little Rev Robotics hex inserts. These are plastic inserts. Oops, I'm not showing that, sorry. So you have the bearing and you have the spacer. My camera is in the wrong direction for me to be able to do this. Let's do it that way. All right. All right. So you have the spacer, you have the bearing, and you have this little hex insert. And what the hex insert does is it can go inside the bearing and it adapts the 8 millimeter inner diameter bearing to be able to go onto a Rev hex axle. So these are all going to be sandwiched together inside of the spacer, and that's what will enable the spacer to be able to spin around the shaft and the wheel and the sprocket as well. So there's a question in the chat, does the wheel have an inner side and an outer side? And the answer is no, it's symmetric, right? Well, it's mostly symmetric. Let me rephrase that. But as far as the mounting points on the wheel are concerned, there's not a difference between the two sides. The two plates are essentially identical. Now, there is a difference in wheels in that for mecanum wheels, there are left-handed and right-handed wheels. And you can see it here as I'm looking at this. The orientation of the rollers is very important for where the wheels go. You can't just put them, you can't just put 4 mecanum wheels on in any orientation that you want and have it work properly. So there is a proper orientation for the mecanum wheels. The short version is that it should make a pattern of an X when viewed from the top of the robot. And what we mean by an X is if this is the left-hand side of my robot, then the back wheel would go here, and the front wheel would go here. And let's see if I can get them to stay still. Probably not. And since this is the left-hand side of my robot, you can see that the rollers are pointing towards the middle. And so this would be correct for the left-hand side of the robot. This would be incorrect for the left-hand side of the robot because now the rollers are making what's called an O pattern. If you imagine there's 2 more on this side, that would be wrong. So you want to make sure that the wheels always make an X pattern. We'll cover that probably more in another future clinic. So anyway, so the wheels are different, that there's a left-hand wheel and there's a right-hand wheel, but there's not a difference in terms of how it mounts onto the axle. So when we're done, we want to be able to come up with something like this. This is what we want, that we can slide onto our axle and then have it spin freely and then hook up chain and drive the robot around. So let's look at what's needed for that. So the first thing that I mentioned is that we need to have bearings for it. Now, Rev Robotics sells a bearing, and they're really nice bearing that they have on their website. They are the, let's see here, let me switch to that. So they are the, let's pull it up there. So they are the 8 millimeter by 12 millimeter by 3.5 millimeter flanged bearing. And it's the flanged part that is important. So the flange of the bearing is that ridge that exists on the outside of the bearing that keeps it from going all the way through a 12 millimeter hole. So on the outside of the bearing is this flange, and I have a bearing here with me. So here's one of the Rev Robotics flanged bearings. If we look at it from the top or from the side, then you'll see that it has this little, where'd my pointer go? I lost my pointer. All right, I'll use this pointer. It has a little ridge here that keeps the bearing from falling through the hole. That ridge is a problem in this particular application because if I take here's the sprocket that I'm going to want to mount, and any of the Rev sprockets are going to have this 16 millimeter hole pattern. If I try and put the flanged bearing on top, what you'll see is that the flange interferes with the holes where the screws are going to go. So because the screws are going to go in there, there's not really a good place for me to stick this bearing where it's going to not get in the way of the screws. And so that's why I ended up needing to go to a not flanged bearing that doesn't have that feature. And so the not flanged bearing is exactly like the Rev one. It's the same diameters, it's the same thickness, it just doesn't have the flange on it. And that one will fit on the sprocket without getting in the way of the screw holes. And so that's why I chose to go with those. Nicely, those are available from Amazon from a number of different sources. So here you can get 4 of them for $6. The ones I got were these, the ABEC 3 rubber seal bearings, 8 by 12 by 3.5 millimeters. And you can see they look just like the Rev ones, except they don't have the flanged part. And so they work out really well. So that's the feature, or the main thing that we're trying to get to, is to be able to make a spacer that can hold the sprocket, that can hold the bearings, and be able to spin properly. So let's go into Onshape and see what we would want to do to make that work. So I'm going to go back to sharing my screen. If I can, share screen. So here we are, looking at the chassis part. And one of the first things we need to do is model the bearing. I can grab the Rev Robotics bearing from the available parts, but it has the flange on it. So rather than do that, I'm just going to create my own bearing model real quick. It's also a good example of how we can use sketches and extrusion. So for the first part of the demonstration, all of these parts that were in this model came from the parts library, where I just pulled them in from the parts library and attached them together. Now we're going to see our first instance of what it takes to create a part from scratch, if there isn't already a part library. Now, somewhere out there on the web, there's almost certainly going to be a 12 by 8 by 3.5 millimeter unflanged bearing model that I could download, but I'm just going to go ahead and create one real quick. So for that, we're going to start by creating a new part. So down at the bottom here, I'm going to say insert a new element, and it's going to ask me what is it that I want to create. And there's a variety of things I can do. I can import a model, I can create a new folder, I can create a new drawing or a new project, I can create an assembly, or I can create a part studio. And so if I want to create a new part, then I'll do that in a part studio. I'm not exactly sure why Onshape calls it a part studio. Probably because there can be multiple parts in it or something like that. But usually I just omit the word studio whenever I see this and say I'm going to create a part. And so along the bottom here, you can see there are multiple tabs that are the different components or different things that I've created. My overall assembly is this tab. My axle assembly is where I created just this part of the assembly. And we're going to add the wheel to this in a little bit. And then within the overall assembly, there were 2 axle assemblies already attached. And so having it as a separate assembly makes that easier. So I'm going to go into my part studio here, and I'm going to just rename this tab to be ABEC 3 bearing, because this is going to be the bearing that I'm going to create. And we can model the bearing to whatever degree we want in terms of, trying to get it to be, pretty exact. But all I really need to know for the bearing is its inner diameter, its outer diameter, and its thickness. So I'm just going to model that. So we're going to start by creating a sketch. So a sketch is a 2-dimensional drawing of one of the features of one of the parts that we want to create. And when you're creating a sketch, you have to define a plane on which the sketch is going to exist. And I'm going to select the top plane. You can see here in my window, as I'm rotating around, there's a top plane, a front plane, and a right plane. And they're all at right angles to each other. But I'm going to select the top plane. And that says, okay, I want to create a sketch in that plane. And you'll see that in that plane now, coincident with the top plane, there's the sketch plane, and that's where my sketch is going to live. And usually what I do at this point is I go ahead and turn off the top, front, and right planes, because they just get in my way. And the next thing I'll do is I'm going to hold down the right mouse button to pull up a menu, and I'm going to say view this normal to the sketch plane. So that turns the sketch plane around so that I can see it head on, straight on, as opposed to seeing it from an oblique angle. While I'm here, because I'm doing this over the web, and just to help those of us who might be challenged with reading the smaller font, I'm going to increase my font size real quick to see if that makes things better in the video when we're done. All right, so to create a bearing, if we look at a bearing, it's just a pair of circles. So I'm just going to create those pair of circles. So there are different tools across the top here for different types of sketches, of sketch elements that we want to create. So we can create a line, which of course is just a simple line. I'll undo these as I go through. You can create a rectangle pretty simply. You can create a circle, and we're about to do that for our bearing. There's also ways to create arcs. There's a way to create polygons, splines, or curved surfaces, individual points, add text. A lot of different tools up here. We want the circle tool. Within each of these tools, there's a drop-down menu that lets you choose the different ways of creating the shape that you want. So right now I've said I want to do a center point circle, which will create a circle by defining its center and its radius. You can also do a 3-point circle, which you give it 3 points, and those identify that the circle is supposed to go through those 3 points. And you can also do ellipses. I'm just going to do a center point circle. I'm going to start at the center and drag out, oops, I lost my circle tool. So I'm going to start at the origin and drag out a circle here, and I just clicked on the origin, and now I can move my mouse, and then I'll click again, and that creates the circle, and it's waiting for me to type in a value for its diameter. So I'm going to put in 8, and that will represent the 8mm inner circle of the bearing. And now I'm going to create another circle, and I can just continue with the same tool, and I'm going to click in the center and drag it out and click again. And for this outer circle, I'm going to type in 12, and these are all in millimeters, and that becomes the outer dimension of the bearing. And now that I've done that, these dimension lines, you can drag them around to make them a little bit easier to see. So my outer circle is 12 millimeters, my inner circle is 8 millimeters, and that's my sketch. So the most common operation that we do when we want to create a new part is an extrude. So we start with a sketch, and now I can exit out and say the sketch is good because I'm done with this sketch. And that takes me back to my main toolbar of all of my different operations for pulling things together, creating parts. And the operation I really want is this first one called extrude. And what extrude is going to do is it's going to take a two-dimensional drawing of some sort, a two-dimensional shape, and give it thickness in the third dimension. So I'm just going to click on the extrude tool here, and I'm going to grab this outer ring. I can grab the inner ring, this inner area, or I can grab this outer area. I'm going to grab the outer area, and as soon as I click on it, then it will extrude it out to make this long hollow cylinder. And so if we scroll around here, you can see it's a hollow cylinder that it's created with that ring. If I click on the inner circle as well, then it would get filled in because it would extrude both of those. And if I click on only the inner circle, then I would just get the cylinder of the inner circle. So whichever areas I highlight in the sketch, those are the parts that are going to be extruded. And since this bearing is going to be 3.5 millimeters thick, I just go into the depth section and change that to be 3.5 millimeters, and it comes out being made 3.5 millimeters. And I can say, okay, that's my thing. And now I have a model of the bearing that I'm going to use. While I'm here real quick, I think I'm going to try and change its appearance. I can just right click on it and select appearance just to make it easier for this one. And so I'm going to edit its appearance, and I'm going to go through and make it, I'm going to make it a goldish color here, like so. Oh, actually gold is the color of my spacer. Let's go purple, has to be a purple bearing. All right. Any questions so far on what I did to create that bearing?
So Patrick, is there any particular reason you chose not to do like a revolute joint in there to show that it can rotate?
I will do that revolute joint when I pull it into the assembly, but I just chose not to make it part of the bearing itself. You can do it that way. If you look at like the Rev Robotics bearings and some of the other bearings that are available, I'm going to switch off the screen here. Then in the models that they create, they actually model, for example, they actually model the inner raceway and then the part that holds the bearings and the outer edge. They actually model that in the CAD model. And then you can have the inner raceway be a revolute joint for the bearing. But for the robot design that I'm doing, the fact that the bearing needs to have a revolute joint is not, it's not terribly important to have that level of modeling as long as I can make it spin somewhere later.
Okay, thanks.
Sure. Any other questions real quick? Okay, let me see if I can get my screen sharing again. So I'm gonna try and do this right. All right. So now that we have the bearing, I'm gonna go back to my axle assembly here. And this is where I'm going to start putting the pieces together for this wheel that's going to take place here. So just to think about the parts that need to come together here. And let me pull up my camera here. Actually, now it's going to be a sprocket. The sprocket's going to be attached to the spacer, and the spacer is going to have the bearings inside of it. So let me start another part for the spacer and put it together, and then we'll look at all the different components of that. Now, as I'm doing the design for the spacer, we can certainly do just a very simple spacer, and then we'll discover it doesn't work. And so I'm going to walk through some of the nitty-gritty details of how to design the spacer so that it can be properly 3D printed and that you can be guaranteed that it's going to work and not run into problems when you're creating the different models. So we're going to start by creating a simple spacer, and then we'll go through and do all the little tweaks that have to be done to really make it a final product, a final worthy part to have things go together. So I'm going to create a new element again, and I'm going to create a new part. And just because I really like to be able to keep these quickly, I'm just going to rename this part. This is going to be the spacer that I will have. And we're going to do a similar thing for creating the spacer in our model. So let's start by defining a sketch plane on the top sketch plane. And I'm going to turn off the other sketch planes here so I don't have to look at them. And I'll say, please view normal to the sketch plane. And so all the view normal did is it took from that side view to get me normal to the sketch plane for the full view. The basics of the spacer is it's going to be a cylinder, right? So we can just do a cylinder. We just saw how we did a cylinder. We just did a cylinder. It's going to have a smaller inner hole. And that inner hole needs to be big enough to hold the axle. So I'll make it 8 millimeters to begin with again. And we need an outer hole, or the outer edge of the cylinder. And for the outer edge, I'm going to make it to be, just a minute, I'm hitting the wrong keys here. Circle, there, like so. And I'm going to make this 24 millimeters in diameter. And now the question becomes, why would you select 24 millimeters in diameter? And the answer is that on the sprocket, if I make this circle any bigger than 24, the chain will no longer fit on the sprocket. So let's go and look and see how I find that out. So if I go back to the Rev Robotics site, I can go to their tech resources. And in First Tech Challenge, what I'm really interested in is their sprocket guide. So I'm just going to go over to their sprocket guide. And you'll see that they have these different components here: the chain clearance diameter, tooth outside diameter, pitch diameter, and so forth. And what we need is the inside diameter. And let me see if they published that here or not, or did I have to get it somewhere else? But just looking at this picture where there's a 15 tooth sprocket here, what I need to do is make sure that the spacer that's there isn't so big that it ends up hitting the chain when it's on the sprocket. So I'm wanting to be very careful that my spacer is not so big that it hits the chain. Yet I still need it to be big enough to be able to hold the screws properly. And so 24 millimeters seems to be big enough to do that. Let me see if the do they have the chain clearance diameters here? I'm used to looking at the older document to be able to see it. They have the chain clearance diameter and the outer diameter, but not the inside diameter. Well, we're just going to go with 24 millimeters for now. I could actually pull up the model of their sprockets and see what the inner diameter is, but I'm just going to go with 24 because I don't want to spend too much time on that. Okay, let's see here. Let me switch back to this. All right, and so now we have our basic cylinder, and I'll just do an extrude operation. There's a shortcut to the extrude operation right here, so I'll say extrude it, and we'll see that it has made a nice little cylinder there that is 25 millimeters thick. I'm good with that in the shape of this, and that's the basic shape of my sprocket, of my spacer, sorry. So that's the first step. Any questions on that so far? All right, if not, then the next part is we need holes to hold the screws for the sprocket. So to hold the sprocket and the wheel to the spacer. So let me just switch back real quick to my camera view again, just to give a really good overview of what this is going to look like. So on the one hand, we're going to have a wheel. We're going to have the spacer next to the wheel. And then we're going to have the sprocket held onto the spacer, and captured inside are going to be the bearings. We'll come to that point in a minute. One of the very interesting things to note about the Rev Robotics sprockets and wheels is that the hole patterns don't match. So the hole pattern on the sprocket is it has 6 holes based on a 16 millimeter diameter circle. And so there's 6 of those. On the Rev Mechanism wheel, there's 4 holes based on that 16 millimeter diameter circle. So if we try to line these things up and attach them together, only 2 holes will line up. So I'm just going to model 2 holes in my spacer. Now the spacer I did before, you'll see it has 6 holes on one side and 4 on the other. But I've since just decided to only have the only 2 holes are going to work. The other part to this that I done for this is that I'm going to hold this all together using 2 screws. So I have these really long 35 millimeter screws that Rev Robotics sells. And so the screw is going to go through the sprocket into the spacer. See if I can get this to go through this spacer or not. Let's try my other spacer and see if I can get it in. I don't want to have to screw it all the way in. Fine. I'm going to screw it all the way in here just to demo it. Plus I get to show off my cool little electric screwdriver here. When my piece 3D printed, it didn't print the holes quite big enough for this to be a clearance hole. So that's why I'm having to screw all the way through it here. All right. So I have the screw going all the way through. And the point of having the screw go all the way through is that now when we attach it to the wheel, there's enough of the screw on this side that I can put a nylock nut on it. And the main thing that I wanted to achieve with that is that I don't want the 3D printed spacer to be responsible for turning the wheel. I could come up with a design where the screws go into the 3D printed spacer and attach the sprocket. And then on the other side, another set of screws go into the spacer and attach the mechanism wheel. But then that means that the force that's needed, the torque that's needed to turn the wheel is the chain turning the sprocket, turning the spacer, turning the wheel. And I don't trust 3D printed parts a lot of times for being able to handle that kind of load, especially on a drivetrain where it's turning things. And not only that, but when we 3D print this, we're almost certainly going to be 3D printing it in this orientation where this is my print bed and going up. And so the layers are going to be around this way. With the spacer. And so if there's a twisting load on the spacer, then you might get layer separation that would cause it to break. So I really wanted to have the sprocket and the wheel directly attached to each other. And so I'm making holes that go all the way through the spacer and out the other side, so that the sprocket is grabbing the screws that are grabbing the wheel, and it's really the screws that are taking most of the force, and the spacer is acting just like a spacer, but it's not actually responsible for transmitting all of the torque to the wheel. So that's the goal that I'm aiming for there. So going back to our video here. So now I need to add those holes for the for where the screws are going to go. So the easy way for me to do that is I'm just going to add them to my original sketch. When I did the extrusion, Onshape and most other CAD packages, after you extrude a sketch, they automatically disable the sketch. They turn it off or make it invisible because they assume you're done with it. So I can go back to my sketch and turn it back on, and now we can see where the sketch is. And I'm going to go edit it. And so I'm going to request to edit it. I'm going to say, please view normal to the sketch plane. Right now it says I'm looking at it from the bottom. I want to look at it from the top. There we go, like so. And I need to add a couple of holes to this for my screws to go through. So that's, again, just another circle. So I'm just going to create a circle out here at the side. I want that circle to be large enough for a screw to pass through it. These are M3 screws, so I'm going to change the diameter of this hole to be the size for a through hole, which happens to be it's 3.404 millimeters. And why 3.404? Well, that's the size Rev uses on their holes. So I just match what Rev uses for their holes to make my circle the same size. I need 2 of them. And I could just use the circle tool and create another circle over here. But instead, what I'll typically do for something like this is I'll do a circular pattern. So a circular pattern is here under the pattern menu. There's a linear pattern for doing things in a rectangle. I want a circular pattern. And that will take an existing shape and replicate it around a center point. So I've selected the circular pattern tool. I'm going to say, please duplicate this circle here, and you'll see that it's created 3 of them, because it says I'm going to create 3 of these for you, and they're equally spaced around this center point. I actually am going to make 6 of them here, just so I could have a 6-hole pattern. And so I've got that. I haven't figured out, there we go. And so now I have this pattern of 6 circles, and they're tied with each other. So if I move one of the circles out, then all of them all move with it. So that's kind of nice. So now I just need to get the diameter between them. Now these circles are the holes on the Rev products are based on a 16 millimeter diameter. So I can go and grab a dimension line, and I'll say I want this center to be 16 millimeters from that center, and I'll just type in the 16, and it moves them so that these 2 circles are now 16 millimeters apart. You can see it's no longer centered on the spacer, and that's because the center of the pattern wasn't attached to anything in the model. So I'm going to scroll in here. Here's the center of the circular pattern. Here's the center of my model. I want those 2 points to be the same. Or another way of saying that is I want them to be coincident. So I can go up to my constraints list, pick coincident, select those 2 points, and it'll put them on top of each other. And the other thing that you'll notice is that when I did that, all the circles turned black. So let me undo that step real quick. Right now they're blue, and the fact that they're blue means they can still move around. There's not anything fixing them in place. These 2 circles are constrained to be 16 millimeters apart from each other, but I can grab one and I can drag the whole thing around in different ways. But I want to make sure that it stays, that it's fixed in place. And so when I do the coincident tool and say this center point and this center point should be in the same location, now they all turn black, and that indicates they're no longer able to move. All right, so and let me just move this dimension line. So now I have these 6 circles, and I know that they're all 16 on a 16 millimeter diameter circle is where the centers of these are. So they're all in the correct spot. So that finishes that edit that I did to that sketch. Now, if I go through and look at my model, you'll see it made holes for all of those circles. And I could leave them all there, but I'm going to fill 4 of them in, just to go ahead and fill 4 of them in. So I can go back and edit the extrude. So I go over to the extrude that was done. I'm going to edit the extrude, and now I can turn on. Let me get a good picture here. I can turn off the circles that I want to have filled in. And so that just leaves the other ones, and then hit OK. And now I have my spacer, and it has the 2 holes in it for being able to do the screws that are going in this model. So let me stop there real quick. Any questions? Am I going too fast, too slow, good speed? You can signal in the participants window, go slower, go faster. Let me know. I see a good, that's good. I have a question. It only does it on the one side. I'm not sure what the question is about. So the sketch is on this side, and when I do the extrude, it's extruding out to this side. I could extrude to the other side. That is a possibility. There's a lot of different ways to do extrudes, and we'll see some of them here in just a little bit. If that didn't answer your question, then give me another rephrase of that question, and I'll see what I can do. All right, so we have that there. Let's go ahead and start putting some of the pieces together now onto our model, onto our axle assembly. Because here's our axle assembly that we had, and this is the outside of the axle, and this is the one that goes on the inside in this to into the thing. And I see a question: how to extrude halfway? We're going to do that here in a second. So I'm going to go ahead and pull in the parts that are needed here. So the first thing that I'm going to want is I'll need a bearing. So for the bearing, I can go in this model and I can say let's insert. And here's my parts studio. This is the parts that I've been creating. Here's my bearing. So I'm going to add that bearing to this structure. All right. So there's the bearing there, like so. And I'm going to attach this bearing onto the shaft. Actually, before I do that, I probably need a rev hex spacer to go inside the bearing. And in fact, that's so common that maybe I should just make an assembly for that. No, I'm not going to bother with that. We're just going to insert. So I need the little hex spacer. So I'm going to go insert other documents. I'm going to go to the FTC robotics parts library, which I signed up for, and others can sign up as well. And this will be in the Rev Robotics section, the FTC section, the motion section. It's a rotary motion part. It's an adapter. And there it is, the 5mm hex to 8mm round bearing adapter. So I'm going to pull that into my model as well. Where did it go? Okay, let me undo that step and do it again. I'm not sure where it went. FTC robotics parts, Rev Robotics, FTC, motion, rotary motion, hubs and adapters, 5mm to hex bearing. Click that. Oh, there it is. It's just hiding in there. I'm going to pull it out to the side. All right, and let's say OK for that. Okay, so I'm going to attach this hex adapter to the shaft. And since the hex adapter won't actually spin, I'm just going to do a whatever this one was called, a fastened mate. So for a fastened mate, we covered the different types of joints in the previous video, so I'm not going to go through it in too much detail. But I'm going to say I want to join this face, that center point there, and I want to join it to this face. Let's see if I can get it right here. This face, its center point there, And so now it's done the fastening. It appears to be off in terms of the rotation, but I'll fix that here in a second. Oh wait, I can probably fix it this way. Rotate it 90. Yeah, that did it. Cool. All right, and so there's the hex adapter that's going to go on, and now I can attach my bearing to the hex adapter, and for this I can do a revolute joint if I want, and that would make the bearing join using a revolute thing. So let's go ahead and do that. So I'm going to join that circle there to the inside of the adapter there. And now you can see that the bearing is there. So that looks good, right? So I have the space, I have the insert and I have the bearing, and this bearing is, you won't be able to see it turn because it's all the same, but this bearing is able to turn there. And now I need to attach my spacer. So let me go ahead and stop there for a second. Any questions about what I did for attaching the insert of the bearing? Now, the next step for us is going to be to attach our spacer, but we need a hole, we need an inset where this bearing can go, because our spacer as it exists right now just has this center hole here, but that one's not big enough to be able to hold the spacer. I could make that hole big enough to, I'm sorry, not big enough to hold the bearing. I could make that hole big enough to hold the bearing, but then it would slide all the way through the spacer. I really want it to be captured or trapped inside of there. And again, I'll go back to my physical model here real quick, just so that we can see the physical model. So you can kind of see inside of this spacer, there's a little ledge inside of there, and that's designed so that when the bearing goes in, it will only go in a certain distance. It won't go all the way through, and I'm having trouble getting my bearing to go in this spacer. Let me try the other side. Yeah. So it won't go all the way through the hole. It'll only go a certain depth in there. So I'm going to go ahead and model that. All right. So here's our spacer, and I need to create that little inset for the hole to go there. So I'm going to go back. I could just create a new sketch to make that hole. I'm going to edit my existing sketch here. And I'm going to say go normal to the sketch plane again. And I like looking at it from the top just because it's easier. I'm going to move this dimension line out of my way for a little bit. And I need another circle here that I can use to create that other hole. So I'll put it there. And I could make this be 12 even, but if I do it 12 even, it's going to be a little too small to hold the 12 millimeter bearing. The 3D printers are not super precise. They're very precise, but if you're trying to get accuracies of more than 1/10 of a millimeter, you're likely to be disappointed. So I'm going to make this circle be 12.1 millimeters instead of 12. The rule of thumb among many 3D printing experts is that if you want something to have a really, really tight fit, then make it 0.1 millimeters bigger. For a snug fit, make it 0.2, and for a somewhat looser fit, make it 0.3. So I'll just make it 12.1. And at that distance, you can now see just how close it is to the screw holes, right? It just barely fits in there, which is why we couldn't use a flanged bearing for this. So that 12.1 is going to be the little inset cavity where my bearing's going to go. I'll close out the sketch. When I close out the sketch, you'll see that it made the hole go all the way through. I don't want it to go all the way through. I want to have a cavity there, but a smaller part on the inside. So I'm going to do it. I'm going to do it two different ways. So first of all, let's do it where we make a hole into the cavity. So I'm going to edit this extrude and turn on this one little section here, so it's back the way it was, right? So this is the way the spacer looked before, and now I just have added this individual circle, right? So that's that part. Now I'm going to do another extrude, not edit the existing one, but an additional extrude. And in this extrude, I'm going to remove material. So you have options to do a new part to add to an existing part, or to remove from an existing part. So I'm going to say remove, and I'm going to click on this area, this little outer ring part that I did here, and I'm going to flip it to cut the other direction. And so now instead of adding material, it's removing it. And I can say, let's remove it for only 3.5 millimeters. And so when I do that, let's see if I can zoom in here appropriately enough. You can see it's making a little cavity in there, 3.5 millimeters deep. And let's just go ahead and do this and turn off the sketch. And so that second extrude is basically saying cut out a circle from the existing part that is 3.5 millimeters deep based on that shape. And we can check real quick to make sure that it is 3.5 millimeters deep. So I can say 3.5 millimeters there. The distance from this circle to this circle, and down at the bottom, it says the difference is 3.5 millimeters between those two circles. So that's just big enough to hold my bearing. All right. Any questions on that real quick? Now, we're going to see some places where this model is not going to work, and I'm going to show you how to fix them, but I'm doing that on purpose to show the fixing part. Let me see if any other questions? No other questions. Okay, so now let's attach the spacer to the bearing in the axle assembly. So now I can go to the axle assembly, and I'm going to grab my spacer and insert it. So here's my spacer, and I'm going to say, give me a spacer. It did, and I'm just going to move it around. Oh, it gave me two of them. I don't want two of them. Cancel. There we go. Like so, and so on. It kind of put it in a funny place there. Let me scoot it over here. And so now this spacer has that little cavity in it that I can use to put on this bearing. So I can just do a fastened mate, because the bearing already knows how to spin. This can be fastened to the bearing. I want to fasten this ring here to this part of the bearing, because that's going to be the part that's inside the spacer. So just very quickly, and I'm choosing these very, very carefully and for specific reasons. But when I press the bearing into the spacer, what I know is that when it's all the way in, this ring, come on, give me just that ring. This one ring here of the bearing is going to be against this ring of the spacer. So those are the two rings that I'm choosing. So let me do a fasten, grab that ring and that ring, and you'll see that it moved the spacer there. It flipped them around the wrong way. So let me flip it the other direction. And now we can see that the spacer, oops, it grabbed the wrong ring. Let me correct that and say, I want it to grab that ring there. That one right there. See if that gets it. Yes, there. And say, okay. And now the spacer, you can see it neatly encapsulates the bearing. So cool. Any questions on that part? Okay, our next step is we can attach the sprocket. So let's go ahead and attach the sprocket to the spacer. I have my own copy of the sprocket because the one that is in the parts library, in the FTC parts library, has a hub attached to it, or it did when I looked at this a couple of weeks ago. So I'm just going to attach my own version of the sprocket. And here's where we're going to see some things not fit together. Before I attach the sprocket, though, let me just point out that the spacer spins because we set the bearing to spin. So the spacer is able to spin around the axle, which is what we wanted. All right, so let's go ahead and attach the sprocket. So insert, and here's my sprocket. And I'll just pull it there. And we can say, okay. And now I'm going to fasten the sprocket, that hole there, to the spacer, like so. And it looks like I need to flip it so that it's in the correct orientation, like so. And we say, okay. And now the sprocket is attached to the spacer. And if I turn it, I can turn it, and it's actually turning the whole spacer as I do that. So here we can see if I grab the sprocket, I'm able to turn it and the spacer all together, and they're able to turn okay. Right, so now it's all starting to come together, except for all the things that we haven't covered yet. So can anybody tell me what's wrong with my model at this point? What's wrong with my model is that the sprocket and the nylon insert are overlapping each other. And there's probably a tool, I haven't found it, there's probably an interference tool in Onshape CAD to be able to locate that. But I'm going to turn off the sprocket
Hey,
visibility.
Patrick,
Yeah.
there is.
Yes.
If you right click on the assembly or if you highlight the items and the under the instance list, highlight the items that you want to look at, and
Okay.
then right click.
Cool. Let's see. So I'm gonna highlight all of those, and I'm gonna right click
And
and check interference.
Yep, check interference.
All right. And right now it's telling me there is interference. Thank you very much. Right. I meant to look that up before tonight and I didn't get a chance to do it.
I found it by happenstance.
Okay. Thank you. So it's telling me there is an interference between the sprocket and the insert, right? And so that's really important for us to know. And let me just turn off the sprocket here, and you'll be able to see that right now the insert sticks out from the bearing. And we kind of knew that, right? The insert sticks out from the bearing, but the sprocket is flush with the spacer. And so what happens is that inner hole on the sprocket isn't big enough to go around the head, the flanged part of the insert. So we have two choices. One is we can make the hole bigger in the sprocket and get a drill it out, and off you go. But that's probably a bit more destructive than we want to do. My solution is going to be, let's get the depth of this hole, of this inset hole, deep enough so that the head of the insert is also inside of the spacer. So let's find out what that distance is there between those two. So I'm just going to click on the face of the bearing, like so. And then I'm going to click on the leading edge, the outside edge of the spacer. I'm sorry, of the insert. And it tells me that those are 1.075 millimeters apart. So I need to add that much depth to my bearing, at least that much depth to my bearing. So let me go and do that. So let's go back to the bearing model, not to the bearing, to the spacer, right? Because I went 3.5 millimeters deep here, but I want this hole to be deeper so that it can accommodate the head of the insert as well. So I'm just going to edit this extrude, and instead of 3.5 millimeters deep, I'm going to go 3.7 millimeters deep. And that makes that hole just a little bit deeper. And so now that that hole is a little bit deeper, when I go back to my axle assembly, and note, I haven't done anything else other than change the hole, but now when we go and look at it, oh, it didn't do it. What did I miss? Did I not actually do it? Certainly I did it. I thought for sure I did it. 3.7, yes. Oh, my joint must not be the way I expect it to be. Let's go back to the axle assembly. Oh, there it is. Oh, I did 3.7. It needs to be thicker than that. It needs to be 4.6. The reason is 3.5 plus 1.2, 1.1, 1.2 would be 4.6. I didn't go deep enough. Okay, let's go back to the spacer. Let's change this depth. Instead of being 3.7, let's make this 4.6. So that goes in a full millimeter deeper than where we were at. Now, if I go back to the axle assembly, you'll see that the head of the insert is now inside of the inset, that little coved out area as well. And so now when the sprocket is on it, it won't hit that because it's flush with the face of the spacer. And we can check those. So I'm just going to do the same step that we did before and see if there's any interference among those parts. So I'm going to right click on them check interference. And it says I've got a little bit of interference here somewhere, probably with my spacer and these little tabs, right? So a little bit of interference here that we'll look at here in just a second, right? But what I just did, if I turn off this, you could see that I made the hole deep enough so that the insert would now be inside the same cavity that the bearing is in. Any questions about that? And I think in that process, just going back to the questions, Peter L. had asked how to extrude halfway of a hole. I think my example of making the cavity kind of showed that, right? That to make that partial hole, you just change the length of the extrude, and that way you'd be able to get a hole that doesn't go all the way through. Okay, so the other part that we're seeing the interference on is between this and the spacer there. Let me just check that interference. Yeah, we're seeing some interference on these little tabs, right? And so if I just hide the spacer real quick and go and look at it, you'll see that the little tabs stick out on the other side of the bearing. And the hole that I made for the spacer didn't account for those little tabs. So I'm going to go back to the spacer and fix that, right? The bearing is here, the insert is sticking into this and it's hitting that part of the spacer. So I'm going to go through and take care of that. I'm just going to make this inside hole a little bit bigger. So I can go back and edit the sketch, and instead of 8 millimeters, I'm going to make it 10 millimeters in diameter, and hopefully that'll be enough to get rid of the interference that I had there. And so we do that. We go back to the axle assembly, and I'll turn the spacer back on, and we'll do that interference check again. So check interference, and it says no interferences, which is good. Right, so we now have the sprocket attached to the we have the sprocket attached to the spacer. The spacer is holding the bearing. Because the sprocket is attached to the spacer, it's trapping the bearing inside the spacer. There's no way for the bearing to get out because it has that one little hole in it. Now we just need to do the same thing on this other side. We need a place for the bearing to go on this other side. So let's go back to our spacer and create that hole on the other side. That can be done with just another extrude. So I'm going to add another extrude here. I need to turn on my sketch that I want to extrude from there. And I'm going to again extrude this circle, and I want it to remove material. But this time I want to remove it from the other end of this spacer. And so there's a couple of ways to do that. The first thing I'm going to do is I'm going to change the length of the extrude. Currently it's blind, which just means a distance. I'm going to say go up to a face and remove everything up to this face. And so now if I look at it, it's making the hole go all the way through the end, and so forth. But I can choose offset distance, and by choosing an offset distance, I can say how much I want it to extrude from. And I want the offset distance to be minus 4.6 millimeters. Let's try that. Like so. Did that do what I wanted? No, not exactly. Let's do offset distance. I'm going to do 25 minus 4.6 millimeters, like so. Is that going to get what I want? No. Let's see. How can I remember how to do this? All right, I'm going to do it this way. Let me start over again. I'm just going to do it with, let's see. I'm just going to do it as a blind remove. And I have to select which part I want to remove. I want to remove that outer circle again. I want to go in the other direction. I want to have a second end position. So that's 2 end positions. So my first end position, I'm going to go a depth of 25. My second end position, I'm going to go the other direction, minus 4.6. Let's try that. See if that does what I want. Nope. Yep, maybe. Okay, I'm going to go 25 minus 4.6 there. There. And so now what I hope to have is, yes, I have the cavity on the other side. So let me go look at that extrude again to kind of explain what I did there. So I wanted this circle, but I didn't want to cut from the sketch plane. I wanted to do a removal from the other side. So I said, remove from the other side, which is 25 millimeters away, and then remove back. So start cutting at a depth of 20.4 millimeters. So what it does is it goes in 20.4 millimeters and then begins cutting all the way to the other side. So that gives me the hole for the other bearing that I'm going to want to have in there. And so now I can just go back to my axle assembly and add those parts in here as well. So for that, I need to have another bearing. So I'm going to copy this bearing and paste it into here, and I will join it to the spacer. So fasten that circle to that circle, and there it is. And I need the hex insert as well. So I will copy the hex insert and paste it into my model. And I will attach it onto the bearing that I just had. Let's see if I can get the right face here. There. And I'm going to attach it to, come on. These inserts are a little bit tricky sometimes to grab. Oops, shift, that's why. That point there, and I want to attach it to this outer face of that and flip it. And so now I have the hex insert there. This one has the same issue that was there on the other side, that you want to make sure that it's inset into the spacer, because the mechanism wheel is going to end up being flush with the spacer. And I'm going to leave it at that for the moment. I'll put the wheels on in a second.
How did you do that extrude again?
Yeah, I'll go back and do the extrude again. There's a lot of different ways to do it. So I'll do it the way I did it, and then I'll do it another way.
I brute forced it when I did it before and just drew another sketch and and doubled the effort. And I want to avoid having to do that if I can and do it that way.
Okay, there's only about a half dozen ways that I can think of to do it. So I'll go through the way I did it, and then I'll go through one more, and then you can figure it out from there. All right.
Yeah. Thanks.
So sure. Any other questions or on that part? But you can see we're getting pretty close to done here, which is kind of nice. Just as a note, right? I've been adding this to the axle assembly. Let's go back and look at the overall robot, the big assembly, and you'll see that each of the axle assemblies has the spacer and the bearings and the sprockets already on them. Because I've been modifying this axle assembly, and there's two of them already on the chassis, every change that I make to the axle assembly is being reflected on these as well. So that's a pretty nice little feature of doing it this way. All right, so back to the spacer. So the question was, how did I make this cavity on the other side? So let me undo the cavity here. I'm just going to get rid of this extrusion here. That might mess up my joint in the other model, but if so, we'll go fix it. So let me delete this extrusion. All right, and so now we're back to the part, and it's only got the removal on one side. Okay, so at this point in the clinic, I went to show another way of doing the cavity cut on the other side of the spacer, and it got a little confusing and convoluted. So rather than put you through that in the YouTube video, I thought I would just reshoot the way that I would recommend doing it now. So if we go to the Onshape, you can see we have our spacer, and if we just turn it around here, it's got the cavity cut on one side, and we want to cut an equivalent cavity on the other side. And what I think I would recommend is just go ahead and create another sketch on this other side. So looking at this side here, we can go and say, create another sketch, and you can select this face as your sketch plane, and that will create a sketch plane on that particular sketch. And one thing worth noting is that when you use a face to create a sketch plane, you automatically get the features of that face as part of the sketch plane. So that's really nice. And at this point, we could, of course, just say that on that sketch plane, we want to create another 12.1 millimeter circle that is the same as the circle on the other side. But I think I'm going to show a better way to do it, and that is that since we already have a 12 millimeter, or we have the circle in this original sketch, I'm going to project it, and that's called the use command in Onshape. There's an equivalent one called project in Fusion 360, and what I want to do is take this circle, and I'm going to highlight the circle over here on the right in the original sketch, and you can see that in my new sketch plane there's a light blue circle being created that is the circle for the that is the projection. So it takes this circle here on the right and it's projecting it onto the sketch plane onto the left. So I'll just click that and we'll see that it's there. And by doing it this way, I can be certain that this circle in my new sketch plane is the same diameter or corresponds exactly to this one. So if I later go back to the original sketch and have to change the diameter of this circle, then the one that's on my new sketch plane will match. And so I've got my new sketch plane there. And now I can just do a remove extrude in order to remove the material on this side for the distance of 4.6 millimeters. So I'm going to say, let's do an extrude. I want to remove stuff from this face, and I'm going to change the distance to remove to be 4.6 millimeters, and we'll see that we end up with the cutaway section just like was on the original side. Also, the nice thing about doing it this way is if we later change the size of the spacer itself, the thickness of the spacer, then this will remain at 4.6 millimeters. So that's my recommended way for creating the cavity on the other side, and we now return you back to where we were in the original clinic. Okay, so let me go back to my axle assembly. Hey, my bearings are still there. Cool, they're still in the right spot. So Onshape was able to figure all that out. Any other questions on that? Is it a similar method doing this by other CAD tool like Fusion 360? Yes, it is. Very much the same. You just create the extrusions, and you can extrude with an offset. You can extrude to a surface. You can extrude for a length. You can have multiple ends. You know, it's very much the same in Fusion 360. That's not a lot different in terms of the overall process to be able to do the extrudes. Okay, there is one other thing that I would like to do with this spacer and point out as we're doing this. We're almost done. And that is that when we go to 3D print this part, it's probably going to be 3D printed in that orientation where the bottom is the print bed and here is the top. And the challenge or the thing to think about when 3D printing this is that 3D printers don't like ledges in midair, right? So there's a ledge here in midair, and the 3D printer can't just like deposit the material in the midair there. It will tend to want to sag down. Gravity will make it want to sag down. You can often do things in 3D printing called bridging, where it's able to bridge over this, but that doesn't work well for curved holes like this. So we want to think about when we're 3D printing always, where is the bottom going to be? And it's pretty clear we don't want to try and print on the curved edge. We want to print on the flat edge. And do we have any overhangs that we have to deal with? So the way that I chose to solve my overhang here is by adding a chamfer. And I never know how to pronounce that word. I don't know what the correct pronunciation is. But this basically bevels a edge. And so I'm going to bevel this edge here. And I'm also going to bevel the edge on the other side just so I don't have to worry about it. And I'm going to bevel it for a distance of 1 millimeter. Should be enough. I can actually find out exactly how much it needs to be beveled. I'm just going to find out the distance between these two rings. Not the center distance. I want to know the outer distance. Let's try the distance between that face. I'm not able to see my face. I'll turn off the sketch. That'll help. So I want to know the distance between that face and that face. Oh, it's still showing me the distance between the centers. Well, I can calculate it in my head. I know this one was 10 and this one's 12.1. So the difference between the two is 2.1, and divide it by 2 is 1.05. So I'll go ahead and cut that there. And I want to cut off or bevel it by 1.05 millimeters, like so. Oh, I can't. no, 1.05 millimeters there, like that. And I'm going to go ahead and do the same thing with the other edge. And what that's doing is it's introducing a bevel. So if we look at this part now, it's no longer a 90-degree angle, it's a 45-degree angle. And same thing on the other side. And the 3D printer can handle printing things at a 45-degree angle at a ledge. Most 3D printers can handle 45 degrees, no problem. And so when it goes to print this moving up, then when it gets to here, it'll make a slightly smaller circle and then a slightly smaller circle and a slightly smaller circle till it gets to the inner diameter, and then continue printing up the rest of the way. And it'll do it on the top, even though we don't need it, it'll also do the 45-degree chamfer there just as easily. So so that's another thing that when you're looking at a 3D printed part, it's always worth just considering, what do I need to do to make sure that this part is actually printable? That shouldn't actually change anything in terms of my other model because I attached to those rings like so. But if we look inside of here, if we turn off the bearing and the hex piece there, then you can really see in there that it's at a 45-degree angle and not the 90-degree ledge that we had before. So that's one other part to consider. Okay, so there we have the design of the spacer done. Let's go back to the overall assembly. Now that I have those spacers on there, I can add my wheels. And I could add the wheels to the axle assemblies directly, but because on a mechanism drive, you have left-hand and right-hand wheels, I'm going to add those separately here. So let's just do insert, other documents, FTC robotics parts from Rev Robotics, FTC motion, rotary motion, wheels, and the mechanism wheel. Which one is the left hand? That one looks like the left-hand wheel to me. And I'm going to go to an assembly and I'm going to pull it in as an assembly. Just a minute while it thinks about that here. All right, and I'll move it there. And now that I have the assembly there, we can attach it to the spacer. I'm going to go to this wheel that's here and select it all, and I'm going to make it into a group. Where's the group icon? Or I can probably just do it this way. Nope, group there. So now that it's all going to be treated as a group, and now when I do the fasten, it will all come across as a single piece. Grab this one face here. There. And go and attach it to this spacer there. And I think that got it right.
Patrick?
Yes.
One of the things that I got stuck on when I was working on this myself was actually figuring out how to remove those nuts and the from the wheel assembly.
Yes.
And I watched your Fusion 360 and tried to use the language from that to Google an answer, and kind of ended up going down a rabbit hole. You don't have to do it right now, but do you happen to know the language so I can go, you know, the Onshape jargon for it so that I can go look up how to do it myself?
So what you want to do is create a modified part.
Okay.
All right. And the reason why it won't let you easily do it in Onshape is because you're pulling in the assembly from the FTC library, and you don't have edit permission to that library. So what I think, there's a way to do it with a modified shape. I haven't found exactly the right way to do that. What I have done in some cases is to just, rather than use the FTC part library, I just go grab the CAD file from Rev directly and load it into my account so I can modify it.
Okay.
And that's another easier way to do it. The other possibility that is worth considering is, don't worry about taking them out, but just turn them off.
Make them invisible.
Yeah, just make them invisible. That's what my lead designer did a lot of last year.
Okay.
Is he would just copy parts and make them invisible. So they're still there. They're still part of the model. But yeah, it won't let you modify it because of because of that. It won't let you modify it because you don't own the part when it's from the library. You could probably copy the part from the library into your own directory and modify that as well. But I do know the key phrase is modified part.
Okay, thank you.
You're welcome. Any other quick questions before we go on? All right, so at this point, it's always good to check for interference, right? Whenever you're adding parts and whenever you're working with such tight tolerances as this, it's good to check for interference. And if we look, after I attached the mechanism wheel to the sprocket, you can see the mechanism wheel is hitting the extrusion that's there, and that would prevent it from spinning. So my solution to that is going to be to make the spacer bigger, to be able to handle that thing. There's also a potential concern here that this sprocket that's here might be hitting this hub. And if we go through and you look really closely, there's like there's a fraction of a millimeter spacing there. So you would want to make sure that there's no friction there, because the sprocket's obviously turning and the hub won't be turning. So you'll want to make sure that there's not going to be any friction there. One way to solve that would be to add some space between the wheel and the hub using a spacer, a Rev Robotics spacer, or just live with it if you decide that there's not going to be enough friction or that they're not going to make contact and so forth. But it's worth always going through and looking at the different parts to see what sorts of interference there could be. So to get rid of the interference between this rev wheel and this extrusion, I'm just going to make my spacer bigger. So let's go back and edit the spacer here, right? And that's not too bad. It's just a couple of extrusion changes. So I'm going to change this extrusion distance here. It was 25 millimeters. I'm going to add 3 millimeters to make it 28. And on the other side, this one here, I want to make sure that I get this one correct. So instead of 20.4, it needs to be 23.4, and that added to the 4.6 will make it 28. So let's do that. And so I just added it, made it 3 millimeters thicker. Now, if I go back to my axle assembly and take a look at where the it's the overall assembly, and take a look at it, you can see the rev wheel is moved farther away. Oh, maybe not far enough. I might need another little bit of space there. So let's go edit the spacer one more time and edit those extrudes. So instead of 28, I'm going to go to 29. And on the other extrude, I'm also going to go to 24.4 here. Oh, there. Okay, good. And go back to my overall assembly. And now we can see that the wheel is pretty close, but it's not going to hit the extrusion. If I felt like I needed more space than that, then instead of making the spacer bigger, at this point I would start trying to move the sprocket over to the left, away from this hub that exists. I also need to be worried about the chain. That make sure that when the chain is on the sprocket, it's not going to hit anything. And there are going to be some screws and nuts. There's some screws heads that go in here to attach the hub to the indexable bracket here, and to attach the sprocket to the spacer. And so those heads might interfere as well. So let me go back to my axle assembly and let's add some of those the screw heads in real quick, just to make sure that we're in good shape there. So for this, I'm going to go to other documents, FTC robotics parts. I don't know if they have the hardware here. Fasteners. Yeah, this one will work. I think it's the 1713. So it's going to insert that. So that's just a simple bolt head. Let's attach it real quick and fasten it where it needs to go. And I don't need to necessarily put all of them in. I just need to put enough in to be comfortable that I'm not going to run into a problem there. I didn't get my connections in. Okay, so there I put the head of that one in. And now I've pretty well convinced myself that when I put screw heads on this side, they're going to interfere with each other. So I definitely need to see about moving this sprocket over to the side. The original joint that I made that did that was the one that attached the insert to this. So I can go and adjust that one if I find it. It's probably this one. Edit there, and that's the 5mm hex insert attached to the sprocket hub. No, that's not the one I want. Maybe it's this one. Let's see if I can find out where these joints are. Not that one. It's not that one. Yeah, maybe it was this one. Edit. Yeah, it is that one. Okay. So I'm going to do an offset here, and I'm going to offset it in the Z direction by 3mm. And the reason I'm choosing 3mm is because Rev sells a 3mm spacer that would work. And it looks like I need to go 3mm in the other direction. There. And so when I move that insert to give it space, apparently I've lost a couple of joints here. So I'll have to fix those undoubtedly when I did that. But let me turn off my spacer real quick. There we go. You can see that I've added 3mm in here, and now let's fix this. Let's fix this joint here, this mate that's there. It says that it lost the reference to it lost the reference on the spacer to where it was supposed to attach to when I redid those extrusions. So if I go up here and say let's reattach to turn off sprocket so I can see. Turn off sprocket so I can see. If I reattach it to that point there, then it should be fine. And now I can turn these guys back on. And now my sprocket is well away from the thing. I've got space there, and the screw heads aren't going to interfere with each other, so I'm in pretty good shape. So those are the kind of things that you want to check on as you're doing your CAD models. Is my team is notorious for forgetting about screw heads. In fact, in the model that we worked on over the weekend, we had a design for a plate that I was getting ready to cut, and then I said, wait, that looks a little close, and modeled the screw heads in there as well, and it turned out there was a screw head right in the middle of a wheel that was supposed to turn. And so it's like, yep, we need to fix that. Okay, so here's the model, and as you can see, it's coming together pretty nicely. The only steps that would be left at this point are to add the other wheels and to add the motors, and I'm going to do that in a separate video because it's getting a little bit late. I'll add a part 3 to just finish out this model and post a link to the completed model. But before I close up, any other questions? Anything else that people would like to see or know about, especially dealing with Onshape?
Hey, Patrick, I got a question. For this whole wheel, spacer, and sprocket assembly, will it, when it start turning, will it like move a little bit inside? Is it possible?
Yes. So I think your question is it possible for this wheel to slide on this axle?
Yeah.
Yes, it is. And so in my actual design on this side, I put a collar.
Oh, okay.
Right. So let me go ahead and add that in just so I don't forget.
So that collar will kind of fix to the axle? Correct.
So I'll go to Rev Robotics, FTC. I think it's motion, rotary motion, hubs and adapters, bearings. Is it here? Let's see. Yeah, it's this guy, the collar. So I added a collar to it. And let me just pull the collar into here. And so the way the collar works is that it has a set screw hole on it. So wow, what a rough design for the collar. So the collar has a little set screw hole on it. Let me see if I can get it there. And so you could take a set screw and you screw it down in there, and that locks it in place onto the onto the shaft or onto the axle. And so to fasten this here, I would go through and say, let's fasten the collar, and it would go, technically it goes on the axle. So I'm going to fasten it to this part here, and then I'm going to change the Z offset. And I'm not sure how far to go there, but I'm just gonna select 15. Nope, let's go 25. But yes, on the actual model, it is possible that the wheel will go left and right on that axle, and so
Okay.
I'm gonna leave it a little bit spaced away. But you can see if I put that on there, it's going to prevent the wheel from sliding to the side.
Okay.
Right.
Yeah.
And so that's again, that's pretty common. Anytime you're dealing with axles, you need collars on them to keep them from going sideways. Now, in this particular model, even if I don't have, first of all, you should have the collar. And whenever you have a collar, you always, or whenever you have an axle and something that could slide along the axle, you want to make sure you have it prevented from sliding in either direction. So on this direction, it won't be able to slide to the right because there'll be a spacer and this part is fixed. So that's going to keep it from sliding to the right. And on this one, the collar is going to keep it from sliding to the left. Because this is a chain drive, however, the chain is also going to want to hold this sprocket in line with the motor.
Okay.
Right. So it won't go too far
yeah.
off, but it could go far enough off that the chain would slip. Yes.
Okay, but even with that collar, you don't want to like too tight, make that collar against the wheel, right?
Right. You just want it to, yeah, you don't want it so much that it pinches the wheel. You just want it so it prevents the wheel from going too far to the left in this case.
Okay. But so when you install, actually have to install the collar first, or?
That's a good question. What I did to install mine, when I did them, do I have my example here? Yeah, give me just a second. Let me go grab my other one. I'll just do it real quick on an actual example and you can see how it's done. Just a moment. Okay, let me switch over to the camera view here so that we can kind of see what's going on here. Overhead. All right, so here's my axle assembly, right? And you can see it looks like the one in the picture, and so forth. So I'm going to loosen the set screws on the motion hubs and take the axle out. Like so. And so now I can slide the axle out. And so when I'm putting this together, there's the axle, here's my wheel. I don't have a 3mm spacer with me, but just presume there is one. So I would put the axle on like so, and then I would put a 3mm spacer in there. Then I would put the wheel on like so. And now on the other side, right in here, I would add the collar. I thought I got a collar out. I brought a collar here so I would have one. Where did it go? I would add the collar. We'll pretend I'm gonna put a bearing on, but pretend it's a collar, right? I would put the collar on and then add the axle, put the axle the rest of the way through. And now that I have all of this together, I would tighten up the axle on the hubs there and there, and then tighten up the collar up against the wheel in there.
Oh, okay. Yeah,
and
it's
then
a little bit inside. Yeah.
Yeah, it's on the inside, and then that would hold it all together, and it would be just fine.
Okay, thank you.
Any other questions?
Yes, one more question. I see that the bracket to hold the wheel assembly is like plastic. Is that strong enough?
So this was I showed this in the previous one, and this is why I'm doing a dead axle instead of a
okay.
axle.
Thank you.
But the short answer is let me pull the thing apart. So yes, if you're looking at the axles or at the brackets, right? Yeah, they bend like crazy, right? They bend a lot, but And if you just put an axle through and have it as a live axle, they'll still bend a lot. But because of the dead axle, because it's attached and securely mounted to each of these, it becomes actually surprisingly strong. So let me get this through here, right? So I've got the axle in there, and I'm going to tighten up the set screws if I can find them. So here's one set screw there. And I mean, the difference is dramatic. And this is actually how my team stumbled on this design a couple of years ago when they were making the design. So now I have the axle in there, and it looks crooked based on the camera angle. It's pretty straight. All right. So, but now if I try and do this, they don't want to bend at all. Right. It's really, really strong. So, I mean, I'm really pushing on this thing to try and make it move, and it doesn't want to move. And the reason is because we've made a box frame here. In effect, right? That this is really wanting to hold these at a right angle. And when my team was creating their drivetrain of this particular design, they didn't have the plastic brackets, but we did have like plastic polycarbonate or acetal sheets, and they were bending left and right, and the axles kept coming off. And so finally I said, hey, could we do it with a dead axle? And we just tried it. We put the dead axle in there, and it was so solid and rigid. So just having that little, just the fact that the axle can't move makes those plastic brackets really work.
Thank you.
Any other questions from the group?
Just wanted to say thanks for putting this on, Patrick. It was a great workshop.
My pleasure. I love doing it. We have more planned. In fact, I had another conversation come up in email earlier today, and it was like, oh, that needs to be a workshop. I forget what it was, but I wrote it down. So
I do have a bit of an advanced topic that perhaps it's an advanced topic. I don't know. It seems a fairly basic function to me, but I couldn't find any guides for how to do it online. I was making like a battery holder, which is something that my team has desperately needed for several years. And I wanted to make it just kind of natively fit into the Rev kind of pattern. And I wanted to copy the pattern off of some of like the Rev C channel and into something that could be 3D printed or used for a laser cutter or whatever. And I couldn't find any way to copy a pattern off of an existing part and into a sketch to do something with it. Is that something that you know how to do in Onshape?
I've done it once before, but I forget how I did it.
I've done it in Inventor and I've done it in Fusion 360, but I couldn't find how to do it in Onshape.
Let me note that, and I won't be able to do it tonight because I don't remember off the top of my head, but let me refigure out how to do that, and I'll just make a short video on it because it'll only be like 5 or 10 minutes if that.
Okay.
And
fantastic.
And I'll post that to the list. Or if somebody else wants to make the video, I'm totally happy with somebody else doing it. Yes, there was a point where I did manage to copy a pattern from one element to another and start to use it to do extrusions.
Yeah, I found guides for how to do it for if they were like inside the same part studio or if they were inside the same document, but I don't know. They were convoluted and 15 steps long and
yeah. So no, I don't have a good answer for that off the top of my head. But what I can say is that it's not super easy in Fusion 360 either. So
yeah.
So that's copying sketches from one place to another is not been something that has been super easy to put together. To the point that I almost never copy patterns anymore. If I have to, I will. I tend to always want to use the circular pattern tool or the rectangular pattern, and I just duplicate whatever holes I'm interested in that way. I know that's probably a little harder to do with the Rev channel, but rather than try and copy their actual sketch pattern, I just recreate the features that I'm interested in with my own little pattern, and then go that way.
Okay, thanks.
Any other questions or comments? All right. Well, thank you all for joining tonight. We'll do another one next Thursday, and I'm still trying to put together a schedule, a calendar of upcoming events, so people will know what they are. I'll probably work on that this weekend, so we can publish them in advance and people can know what to look for. If you have specific topics you'd like to see covered about anything FTC related, whether it's building, designing, programming, things like that, send them to me via an email. And I'll try and get them on the list and see if I can do either a workshop session like these have been, or just a short little video vignette to be able to cover a lot of those. Thanks again for joining. Have a good evening, have a good weekend, and we'll see you all next week.
Thanks a lot.